Yes, better. No? Yes, better now. So good morning, everybody. Today is the final day of this conference. So, and the first speaker, we have in this session two invited speakers. The first one and the second one, and then another two talks, and then the poster session, then the final session, and after that the lunch, and the conference will be over. So now for the first one, the first invited talk is going to be given by Professor Manuel López-Amo. It's for me a pleasure to present him. He has been full professor of photonics with electrical and electronic engineering department here in the Public University of Navarra, Spain, since 1996, so a lot of time. And he's an IEEE senior member, and he's currently the head of the Optical Communications Group of this department, and also the chairman of the Optoelectronics Committee of Spain, the director of engineering faculty, and of the Electrical Electronic Department of the University Public of Navarra. He has been the leader of more than 60 research projects, and he's co-authored more than 400 works in international reference important journals and conferences. Also, he has supervised 18 PhD theses about photonics, and he is the Spanish representative of the expert committee in International Technical Commission, subcommittee 86C, working group 2 on optical fiber sensor. And the next speaker is going to be also belong to this committee. So please, Professor, when you want.
Thank you very much, Ignacio. It's a pleasure. And to accept the invitation of this conference, I'm going to take the microphone better. Thank you. And well, this presentation is related with the application of fiber optic sensors in smart cities, and it's some kind of compilation of our work. When I say our, it's the work of my PhD students and my research assistants in some projects that we have carried out along the last 10 years, more or less. So, thank you to all the PhD students that are in the presentation, and I am going just to give a quick view of what we have done related with the smart cities, because this, our group belongs to the Optical Communication Group, belongs to the Institute of a Smart City, and the local of this institute is this building. I am going to start with an introduction, very short, talking about things that you know for sure, because you are a specialist on optical fiber sensors, so nothing that I am going to talk at the beginning is new for you. And afterwards, I am going to try to introduce the possible application of fiber optics in small cities environment. So, all of them knows about the advantages of optical sensors. I am not going to try to convince you because you are convinced of that. But I want to remark a pair of things. The size. You know that optical fiber sensors are really small, and it is useful for certain applications, for instance, for biomedical applications. It is an advantage in comparison with traditional sensors. But also, now we have another advantage that the cabling is easier in comparison with conventional sensors when you have to attach a lot of sensors in an structure, and it is very important in smart cities environments. Also, if needed, optical fiber sensors can be a part of the cavity of a fiber laser, and in terms of optical signal to noise ratio, yesterday Professor Íñigo from Malaga were talking about the importance of signal-to-noise ratio in our systems. Well, you can transform a network, a fiber optic network that is used to multiplex sensors into a laser and obtain very good signal-to-noise ratio. Drawbacks of sensors, by now the cost, but it is not true. If you have to attach a number of sensors to a structure, the prices are competitive in comparison with traditional sensors. So, all of you, knows about the difference of sensors if you take into account if they are located in a position, we call them point sensors. If you have a distributed sensor that uses in bridge-in or acoustic sensors nowadays. And also, you have an intermediate option that it is the multi-point sensor network, typically using quick fiber brag ratings. When to use any kind of these sensors? Well, point sensors have advantage with distributed one. Just a great advantage that with point sensors you can measure any kind of parameter, even chemical parameters that it is very difficult to measure with distributed sensor. So we have hundreds of applications in structural health monitoring in smart cities where point sensors have to play a role. Usually the main parameters to be measured are temperature, strain, and vibration, but I insist that you can measure whatever you want. With distributed sensors, okay, the good thing is you use just a cable, an ordinary single-mode fiber cable. Well, if you are talking about temperature distributed sensors using Raman effect, there the cable used to be multi-mode fiber, but anyway, are commercial telecommunication fibers, and you can measure temperature, strain, even vibration, if you, in the case of DAS distributed sensors. The fiber is the transducer, and it is good to monitorize, just measuring these three parameters, to monitorize a very big structure as a bridge or a tunnel or so, or pipelines. If you want to multiplex point sensors, even distributed one, you can use several techniques. Of all the possible techniques, the most utilized are wavelength division multiplexing, that it is used for multiplex fiber brag ratings, for instance. Time division multiplexing, that in combination with the first one is used also to multiply weak fiber brag ratings. You can use also the modulation of electrical frequencies to interrogate, oh my God, to interrogate this kind of sensors. And also, you can use coherent division multiplexing. It is not usual. It is not very usual, but it's used in some applications. I will show you, if I have time, at the end of the presentation, one of these possible techniques. And also, in case of measurement high voltage or high current application, polarization multiplexing is also useful. Okay. In the presentation, I am going to talk mainly about wavelength division multiplexing. Also, very important, optical fiber sensors networks are powered because of the utilization of components for telecommunications. For instance, splitters, couplers with an input and a number of output, are really cheap nowadays, thank you to passive optical networks used in telecommunication. But also happen with the isolators and other kind of optical amplifiers that are very important also in multiplexing of sensors nowadays. So topologies and components used in networks of sensors are typically components coming from telecommunications. The most famous point rating, and I finished the introduction with this, you know, because all of this is known by you, is the fiber brag rating. The fiber brag rating is a periodic repetition or alteration of the refractive index of the core of a single mode fiber that is able to reflect just a wavelength. This wavelength depends on the separation of this maxima and minima of the perturbation of the refractive index. And if, for instance, if you elongate, you apply a strain to the sensor, the wavelength, the reflected wavelength is going to move with the strain. But the same happens with variation of temperature applied to the grating. If you apply heat, the separation between the maximum and minimum are going to increase, and the, oh my God, and the reflected wavelength is going also to move correspondingly. Well, it is the typical application of this kind of devices to measure or whether temperature or strain variations. There's a lot of commercial equipment to interrogate this kind of sensors. And it is an important sensor. Depending on your application, you have more powerful or less powerful interrogator. The prices are getting really low. You have brag rating interrogator of $2,000 nowadays, with integrated optic components from Redondo Optics, for instance. But also you have expensive equipment from, for instance, Micron Optics, with up to 8 channels, and each channel can host, I'm going to show you the numbers now, a number of Bragg ratings. The most efficient interrogators use a tunable laser and also a tunable filter synchronized with the laser. And you can interrogate a number of sensors. How many? Well, depends on the expected variation of the movement of the reflected wavelength of the sensors. If you expect a big variation, typically, for instance, you have a variation of 2,500 microstrains. That means that it is correspond to a shift of plus minus 3 nanometers. And because you have a tunable laser that covers about 36 nanometers, that means that you only can apply 6 gratings in each channel. But if the expected movement of the wavelength is lower, you can have till 20 gratings in the same channel of the interrogator. So depending the expected performance of the sensors, you can attach more or less gratings in just a channel. Topologies for multiplex gratings. Well, the typical ones are, the most used is the serial bus. Okay, an array, we can also say it's an array of gratings. It is the best one because you only have a cable with the sensors, and it reduces the cost of installation of the sensor, that it is very important. But also using the telecommunication couplers of one input and M outputs, uses in passive optical networks for rich hour houses, you can multiplex with no problem the Bragg rating in an star configuration. It is important because these components are really cheap nowadays. And also, the good thing of the Bragg ratings, it is that the information, as I told, is coded in the wavelength shift. That means that it is, these sensors are immune to power problems. I mean, the decrease of the power of the laser, or somebody has bent the fiber too much in the installation, a problem like this. The information is coded in wavelength, and it is protected against certain problems that, for instance, time division multiplexing sensors have. So now I'm going to talk about the title of the presentation, that it is about the application, the possible applications of fiber optic sensors in smart cities. If you read technical papers about the smart cities, not political ones, but technical people divide the application of sensors in smart cities in 6 fields. Building a home to help to the new buildings to work correctly and in an intelligent environment. Also, problems with mobilities in cities, that it is very important. Energy, optimization of energy generation and transportation in cities. Water quality and control, and also waste. I am going to talk about the first 4 applications because we don't have, by now, activities in waste. Also, of course, communications are really important in smart cities because you have to interconnect all the sensors and all the applications of the city with typically with a central control system. So the first application we carried out related with the smart city was this application that it is optimal for fiber optic sensors. Why? We had to demonstrate that this new type of glass designed by an architecture company in Pamplona worked properly in the facade of a tower. This tower was a very special one. Well, the first thing, which are the special characteristics of this glass? This glass has bubbles of plastic. The target of these bubbles of plastic is to avoid people watch what is inside of the tower. And which were inside of the tower? There were antennas. There was plenty of antennas because it was the telecommunication tower of the Public Company of Telecommunication of Navarra government. And the installation of this tower was carried out 10 years ago when there's some kind of hysteria with radiation of antennas. People thought that the radiation of the antennas causes cancer and things worse than cancer. Okay, do you remember this period? Okay, so just in this period, government of Navarra decided to put this tower, plenty of antennas, close to houses. Okay, so they decided to put this kind of glasses that allow you to see what happened inside. You cannot see the antennas inside. Thanks to these glasses, you cannot see what is inside. But in order to check the behavior of this new glass, they have to monitorize the deformation of these glasses with heat and vibrations and so. And because this tower is plenty of antennas producing electromagnetic radiation, you cannot use classical sensors. This tensiometric gauge doesn't work because of the radiation of the antennas. So optical sensors are the perfect sensors for this kind of application. And we were checking with these sensors of micro-optics, we were checking the behavior of these glasses along a year. Okay? We also put a vibration sensor in the roof of the tower because in Pamplona we have some kind of earthquakes, not very big, but typically a pair of earthquakes per week, and so we were checking this. And we have this result along the year. If you check the results along July and August of 2009, you can check that we have temperature variation up to 60 degrees in the facade, okay? And that means deformations, strain deformation, up to, not too much, between 2050 or so and minus 2050. Not very big strain deformation. That was good results from the architecture studio that contracted us. Second application that I want to talk about, the application of optical fiber sensors in energy applications in cities. This slide obviously is not a city, it is the new ITER International Thermonuclear Experimental Reactor that it has been building now these years. Well, the project is delayed, 3 years delayed. The project is going to be installed in Cadarache in France, in the south of France. Well, they have political problems to obtain the license to operate. But anyway, the construction advanced correctly, and they decided to put more than 1,000 of sensors to control the working of the thermonuclear reactor when it works. And the good news is that 80% of the sensors selected were fiber optics. As I told you, the higher the number of the sensors are, the better to use fiber optics, even to measure ordinary things. Okay? The contract was awarded by Smartec, a consortium of Smartec and Fiber Sensing that are well-known companies in optical fiber sensing. One from Swiss, and another one from Switzerland, and another one from Portugal. More modestly, we have some applications developed in smart cities in energy. For instance, some years ago, in 2019, we apply fiber Bragg ratings also to solar panels, metallic structures. Okay, we were contracted by this company, STI Norland, in order to check the behavior of a new structure to hold solar panels. Okay, and we deploy just 43 fiber Bragg ratings in order to control the deformation of the structure with wind. I mean, there are a lot of videos in YouTube where you can see that when the wind is too high, this structure flies with the hurricanes and things like this. So they have to control the design of the structure and if they are solid enough to support. So we check the structure in the lab, also with distributed sensing, with Bragg ratings. We demonstrate that Bragg ratings are as good as distributed sensing for this application. And afterwards, we check it in real life. I mean, this structure is installed in the Bardenas. The Bardenas is a kind of desert we have at the low part of Navarra. At the bottom is a very sunny place. And well, we deployed the sensors, and they were taking measurements along some weeks, a long time ago. Here are the torsion and the formation of measuring of the 3 arrays of these solar panels, and we gave the results to the company, and theoretically, I think they are satisfactory for them, I hope. It is because there are more solar panels in everywhere. It's another application. You can control the formation of the panels, but also the temperature that these panels are suffering in the working day. Other application. We have developed applications in mobility. Indeed, we have in this campus, in this building, we are here in this building, Jerónimo Allianz. So in Los Tejos building, that where are the rooms of most part of us, of the professors of our group and so, well, we deploy a connection of optical fiber to the street. And in the street, we deploy arrays of brake gratings in order to control the traffic in this street. It's called Avenida Catalunya. And we deployed brake gratings, but also special fibers, multi-core fibers and so. So from our lab, using a micro-optics brake grating interrogator, we check the traffic in this street. And for instance, we collect the records of traffic along the day. For instance, we have a peak of people coming using the street at 9 o'clock in the morning. Probably you have realized. And afterwards, the next peak is about 15 hours, and another peak at the end of the day when people goes out home after teaching in the afternoon session. So we are quietly in our lab, and we can measure the traffic in the street. When you see a peak, that means that, well, 2 peaks, that means that there's a car passing through the array. Okay, we also deployed multi-core fibers. These fibers, when we use specialty fibers, are always from France, from Limoges. There's a group called Slim that has a wonderful drawing tower in Limoges, and they fabricate for us multi-core, hollow core, and any kind of special fibers. So we also have measured the traffic with these multi-core fibers, and indeed we are working towards having an application of weight in motion. I mean, you can control traffic with radar, you don't have fiber optics, and you have to install the fiber optics, to measure the traffic. But the advantage of our system is it's possible to weight the traffic or the vehicles passing through the street. And it is important mainly for control the overweight of trucks. I mean, there are legal limits for the weight that the truck can transport. Is 20 tons, I think. Danny, is 20 tons? Yeah. So, but there are a lot of trucks that don't accomplish this limit, and they destroy the streets and the roads. So, if you have a system installed, perpetually installed, you can control and you can prosecute people avoiding the law. Indeed, we have carried out a new spin-off for traffic monitoring control. The spin-off is called Menditech, and now they are deploying a lot of sensor systems. They have their own technology. For instance, they have put sensors all around this campus in order to control the traffic in this area of the city. Another different application of fiber optic sensors in smart cities. Related application related with water. Again, using these wonderful fibers from SCLIM, this group of Limoges, France, we have developed humidity sensors. In collaboration with the sensors group, we have deposited intelligent materials inside the holes of these specialty fibers. And, well, we are able to measure humidity in the atmosphere, but also in the soil. And because we are in relation with people from agriculture science degree, they identify as important as to control the humidity level of grounds or soils in the cities. So, using a structure so small of 500 microns of length, we have interferometers that we are able to interrogate using the fast Fourier transform. You know, if you have this periodical signal in the spectrum, optical spectrum, you can pass to the spatial frequencies and transform each sinusoidal behavior in peaks in the spatial frequency domain. And in this way, you can multiplex in the same structure a number of sensors, okay, by giving different lengths to this structure, and you can identify without problems. So, it is important to control the degree of humidity in soil. In smart cities platforms. So, with this kind of sensors, you can give this information and control the irrigation intensity of all the systems. So, we have developed a multiplexing networks. Important, you have to amplify the sensors, this kind of sensor, in order to achieve with signal-to-noise ratio. But with typical couplers used in telecommunications, you can multiplex the number you want of this kind of interferometric sensor. Here is the response of the multiplexing sensors of 6 sensors, complete disaster in the optical spectrum domain, but if you apply the fast Fourier transform, you have wonderful peaks where you can measure the variation of the humidity of each of the sensors you have. Important, we are using optical interrogation, this micro-optic interrogation we use for rack rating interrogation. It's possible to use also to interrogate this kind of interferometric sensor, because you can do the fast Fourier transform in real time with this equipment. Indeed, micro-optics gives you a software to measure in real time this kind of periodical repeated sensors. So, just for finishing the presentation, what we are involved now? Well, from last year, we are constructing a measuring of quality HAT close to our river. We have a river crossing our campus. It's a real small river, okay? But when the weather is not very good, well, this river can carry a lot of water, okay? Sorry because of the quality of the images. But there are days that the river is not very quiet. And the water is not very clear, neither pure, and you have things to measure, okay? So, we have installed a small hut, a small little house, to control the quality of the sensors. This hut is connected via optical fiber, again with our lab in Los Tejos building, where we have all the equipment, okay? So the equipment is not here, could be stolen there, but the expensive equipment is far away, connected by optical fiber with our building. And, well, there we have this kind of sink of container for water. We have a pump in the river, and we pump water to this container. So most part of sensors are safely inside the height, where we pump this horrible water, and we measure there the quality. We have conventional sensors. It is a system of conventional sensors that measures everything, oxygen, turbidity, whatever is needed for water measurements. But also we are developing our own sensors. For instance, here is a sensor from University of Cantabria for checking bacteria inside the water, okay, with image recognition, I think, no? Okay, but we are also deploying our sensors. For instance, in the last conference of a week ago in Porto, we presented turbidity measuring sensors using capillary fibers, okay? and artificial machine learning. Okay. Also, we have developed in collaboration with Aveiro University pH sensors with panic coating, suitable also to be deployed in these sensors. So, if when needed, if possible, we deploy our sensors here. I mean, it is safe. But there are some sensors that you cannot put in this container because you have to measure in the river. For instance, it's very important for people controlling water quality to measure the speed of the water in the river. What we have done, we have developed a sensor using Bragg ratings, the deformation of Bragg ratings. Depending on the speed of the water, the deformation is higher or lower. So we have checked it in hydraulic labs here in Edificio de los Olivos. And afterwards, we were checking, summer ago, we were checking with a strange structure how to handle these kind of sensors of water speed in a real river. We invented this strange structure, and finally, a month ago, we deployed this structure with just a Bragg rating inside to measure the river quality, but the important thing is to protect the sensor, because real-life applications means that you have to take into account everything. I mean, you have to expect a Coca-Cola can floating along the river, and when I say a Coca-Cola can, is the funniest possibility, because when we visit these kind of plants that renew the water, they have find any kind of objects floating in the river. Okay, so that's we are involved now related with intelligent environment. Now, I were thinking of talking about remote measurement, but Nacho Mate is going to kill me, so I'm going to avoid to talk about this application. Thank you very much for your patience. Very important, I want to thank to this collaborator, including Universidad de Cantabria, in this presentation.
So thank you very much. So now it's time for probably one question. Any question? Okay, so I have, okay, please.
¿Y de aquí?
Thank you very much for that. So can I ask about the reliability and the durability of fiber optic sensors? So you have installed a lot of sensors in the real world, but so have you had trouble about the sensor broken?
Well, it is a very good question, because we installed, for instance, the fiber in the asphalt in the road. It is, well, we were the first one, and we didn't know what were to happen. And we installed the first one about 7 years ago, more or less, no? And they're still alive, so surprisingly, we didn't expect it, okay? Yeah. But it was a surprise. I have to confess that we didn't expect it. Because we are using a very good and very expensive adhesive, epoxy adhesive, special for this application. Mm-hmm. It's expensive, but it survives.
Any other question from the audience? So thanks again.
Thank you.